we introduce a mathematical framework for generating convex approximations of contact models. We integrate into this framework validated engineering-grade contact models with Coulomb friction. With a focus on physical accuracy, we rigorously characterize our approximations, detailing their strengths and limitations. Our novel hybrid approach enables fully differentiable solutions with complex contact geometries implemented in the open-source toolkit Drake. Frictional contact in multibody dynamics presents challenges including non-unique solutions, numerical instability, and local minima. Convex approximations help address these, allowing for robust, efficient simulations. However, limitations persist. For example, Anitescu-based formulations can exhibit gliding in sliding contact, especially at large time steps and slip velocities. Compliant models have better numerics, but require unfortunate trade-offs between dissipation and gliding. These methods also lack flexibility, as the contact model is intrinsic to the formulation, limiting sim-to-real accuracy. Our work resolves these issues by incorporating experimentally validated contact models into a convex framework. Building on our previous work, we frame this as an unconstrained convex optimization problem for the velocities of the system. The optimality condition here enforces momentum balance using a stable symplectic scheme. Our framework allows for custom convex costs to approximate various frictional contact models. Our optimality conditions apply to contact fields that are gradients of a scalar function of velocities, called an incremental potential. Thus, the contact fields must be irrotational vector fields, a requirement that can be succinctly stated as the curl of the impulses must be zero. We derive the conditions that allow us to satisfy this criterion and solve the corresponding partial differential equations to incorporate popular contact models. Additional Hessian-based conditions ensure convexity. The predictive capabilities of the method are demonstrated by simulating the unique gearing mechanism of the BarrettHand, which relies heavily on friction and stick-slip transitions. In this system, a single motor drives both the proximal and distal links of a finger through a coupled gear arrangement. The proximal gear rides freely on internal threads along the shaft of the adjacent worm gear, with Belleville washers at the end acting as a clutch. When the washers are compressed by contact with the proximal gear, stiction holds the proximal gear stationary relative to the worm gear, transmitting torque to the proximal link. When the proximal link finds an obstacle, a predefined external force limit is reached, causing the proximal gear to slip and disengage from the washers. At this point, motor torque is transferred solely to the distal link. Stiction between the worm wheel and the worm gear prevents backdriving, keeping the proximal link stationary. We demonstrate end-to-end differentiation through contact using an out-of-the-box implementation of contact-implicit iLQR using Drake. In our example, a Canova Gen 3 robot arm efficiently plans a trajectory to move a ball to a target position on a plane without predefining the contact sequence. Our hybrid approach uses automatic differentiation through the geometry engine and propagates gradients analytically to reuse factorizations from contact resolution. Our method naturally extends to supporting frictional contact with deformable bodies. Here, we simulate deformable fin-ray gripper fingers on a panda arm in a peg-and-hole task. The robot, teleoperated with a 6 degree of freedom space mouse, completes the task using differential inverse kinematics and a 10 millisecond time step, successfully inserting a rigid peg into a fixed holder. We thank you for listening and encourage you to read the full paper for more details.